Okay, so we have a new energy problem here. We are gonna have a cliff and a valley. This is a 170-meter drop off for a cliff. And at the top of the cliff, we shoot some kind of a giant gun. I guess it'd be some kind of a cannon or something, because the mass it's going to shoot, well, you could say it's a small cannon. The mass is going to be 160 grams. Not kilograms, just grams. So it's really kind of too big to be a bullet or anything, but we're going to shoot it straight up, and it's going to, well, not almost straight up, but it's going to go like this in slight of an arc, and it's going to come down, and when it hits the ground at this location, the bullet's velocity at this location is going to be 90 meters per second. But way up here, the initial velocity of the bullet is going to be 110 meters per second. Now, I know what you're thinking. You're thinking, how can this possibly be if it's at a higher location with a larger velocity? Surely it must be going faster when it reaches a lower height. Well, the question is, how much energy is lost to air friction? Okay, well, the way we're going to do this is we are going to say initial energy equals final energy, and we're going to slightly amend this equation, right, to add our gain and our losses. So we can say EI plus work gain, that's how it goes, the equation, plus EF plus work lost. Now in this case we don't have any work gain. That would be like for a rocket type of a situation. But we do have work lost to air friction. So let us see what we can get. What types of energy do we have initially at the initial location here? Well, we have height, mgh, plus we have kinetic energy, 1/2 mv squared. So we have initially mg hi plus 1/2 mvi squared. Those are the two types of energies that we have. Okay. Finally, we don't have any gravitational potential, but we do have kinetic. Plus our work lost. So, to find our work lost, we simply take this term, take it to the other side, and we get mghi plus 1/2 m. Now, I can factor out the 1/2 m from these two terms when I put it over there, and I get this minus this. And that's going to be W lost. Now, if we plug in our values, this is going to be 0.16 kilograms times 9.8 newtons per kilogram. Let's see, what did I do here wrong? Just a sec, let me ask my students. What have I done wrong? Yeah, there's nothing wrong there. The initial velocity is on this side and final velocity is on this side. And if we take this term to that side, then it becomes initial minus final. Yeah. No mistakes. So now we multiply. We're still here on h. Our h is initial height was 170 meters plus 1/2 times the mass of 0.16 kilos, and then we multiply by 110 meters per second squared minus, finally, 90 meters per second squared. And what do we get? Well, we've got our trusty RPN calculator here. So let's go 0.16, enter 9.8 times. Let me try that again. 0.16, enter 9.8 times 170 times. Okay. 0.5, enter 0.16 times 110 squared. Uh, 90 squared minus times add. Now we're getting 586. 586.5, or yeah, 0.6, 586.6 joules of energy lost to air friction. Okay, and that's the end of this problem. Thanks for watching.